The history of atomic nucleus research is a fascinating journey that has shaped our understanding of the fundamental building blocks of matter. In the early 20th century, Ernest Rutherford conducted the famous gold foil experiment, where he discovered the existence of a dense, positively charged nucleus at the center of an atom. This groundbreaking experiment laid the foundation for further exploration into the structure of the atom. Following Rutherford's discovery, scientists such as James Chadwick and Niels Bohr made significant contributions to our understanding of the atomic nucleus. Chadwick's discovery of the neutron in 1932 provided crucial insights into the stability and composition of the nucleus, while Bohr's model of the atom with electrons orbiting the nucleus helped explain the behavior of atoms in chemical reactions. One of the most remarkable achievements in atomic nucleus research was the development of nuclear fission by Otto Hahn and Fritz Strassmann in 1938. This discovery paved the way for the harnessing of nuclear energy and the development of nuclear weapons. The Manhattan Project, which culminated in the first atomic bomb detonation in 1945, marked a turning point in human history and highlighted the immense power contained within the atomic nucleus. In more recent times, advancements in particle accelerators and detectors have allowed scientists to probe the nucleus and its constituents with unprecedented precision. Experiments at facilities such as CERN have led to the discovery of new particles and the validation of the standard model of particle physics. These endeavors continue to push the boundaries of our knowledge and open up new avenues for exploration in the realm of atomic nucleus research. The discovery of elementary particles has been a cornerstone of modern physics, revolutionizing our understanding of the universe at its most fundamental level. One of the earliest elementary particles to be identified was the electron, a negatively charged subatomic particle found in all atoms. British physicist J.J. Thomson first discovered the electron in 1897 through his experiments with cathode rays, leading to a paradigm shift in the field of particle physics. Another significant milestone in the discovery of elementary particles was the identification of the proton by Ernest Rutherford in 1917. Protons are positively charged particles found in the nucleus of atoms, and their existence helped to elucidate the structure of the atomic nucleus. In 1932, James Chadwick discovered the neutron, a neutral subatomic particle that, along with protons, constitutes the nucleus of an atom. The discovery of the neutron was a crucial step in understanding nuclear reactions and the stability of atomic nuclei. The quest to uncover new elementary particles continued with the development of particle accelerators, which allowed scientists to probe matter at increasingly smaller scales. In 1947, the muon was discovered by Carl D. Anderson and Seth Nettermeyer during cosmic ray experiments. The muon is a heavier cousin of the electron, with similar properties but greater mass. Its discovery challenged existing theories and paved the way for further exploration into the realm of subatomic particles. The 1960s and 1970s witnessed a surge in particle discoveries, with the identification of mesons and baryons, which are composed of quarks, the building blocks of protons and neutrons. Quarks were proposed by physicists Murray Gell-Mann and George Zweig in the 1960s to explain the properties of newly discovered particles. Quarks come in 6 different flavors: up, down, charm, strange, top, and bottom, each with specific properties that contribute to the diversity of matter in the universe. The discovery of the Higgs boson in 2012 at the Large Hadron Collider marked a significant milestone in particle physics. The Higgs boson is a crucial piece of the standard model of particle physics, responsible for giving mass to other elementary particles through the Higgs mechanism. Its discovery confirmed the existence of the Higgs field, which permeates the universe and interacts with particles to impart mass. The exploration of elementary particles continues to captivate scientists and inspire new generations of researchers to unravel the mysteries of the subatomic world. The structure of the atomic nucleus is a complex and fascinating realm that holds the key to understanding the behavior of matter at its most fundamental level. At the heart of every atom lies the nucleus, a tiny yet incredibly dense region that contains protons and neutrons bound together by the strong nuclear force. The size of the nucleus is remarkably small compared to the overall size of the atom. For example, if an atom were the size of a football field, the nucleus would be about the size of a pea placed at the center. This highlights the incredible density of the nucleus, where most of the mass of the atom is concentrated in a minuscule volume. The number of protons in the nucleus determines the element to which the atom belongs. For instance, an atom with 1 proton is hydrogen, while an atom with 6 protons is carbon. The number of neutrons can vary within the nucleus of a given element, leading to different isotopes with the same number of protons but different numbers of neutrons. Isotopes play a crucial role in various applications, such as nuclear medicine and radiocarbon dating. The stability of the atomic nucleus is governed by the balance between the strong nuclear force, which holds protons and neutrons together, and the electromagnetic force, which repels positively charged protons. In some cases, nuclei can be unstable and undergo radioactive decay, emitting particles such as alpha particles, beta particles, and gamma rays. This process transforms the nucleus into a different element and releases energy in the form of radiation. Scientists have developed models to describe the structure of the atomic nucleus, such as the liquid drop model and the shell model. These models help explain the behavior of nuclei under different conditions and provide insights into nuclear reactions and nuclear energy production. The study of nuclear structure continues to be a vibrant field of research, with advancements in experimental techniques and theoretical models shedding light on the mysteries of the atomic nucleus. Elementary particles are classified into 2 main categories, fermions and bosons. Fermions are particles that have half-integer values of spin, such as electrons, protons, and neutrons. They obey the Pauli exclusion principle, which states that no 2 fermions can occupy the same quantum state simultaneously. This principle is fundamental to understanding the behavior of electrons in atoms and the structure of matter. Bosons, on the other hand, have integer values of spin and do not obey the Pauli exclusion principle. Examples of bosons include photons, gluons, and the recently discovered Higgs boson. Bosons play a crucial role in mediating fundamental forces in nature, such as the electromagnetic force carried by photons and the strong force mediated by gluons. The classification of elementary particles extends further to distinguish between quarks and leptons. Quarks are the building blocks of protons and neutrons, coming in 6 different flavors: up, down, charm, strange, top, and bottom. Leptons, on the other hand, include particles like electrons, muons, and neutrinos, which do not experience the strong nuclear force. The standard model of particle physics categorizes elementary particles based on their properties and interactions. According to this model, there are 12 fundamental fermions, divided into 6 quarks and 6 leptons, along with 4 fundamental bosons, responsible for mediating the electromagnetic, weak, and strong forces. The discovery of new particles, such as the top quark and tau neutrino, has expanded our understanding of the particle zoo and the underlying symmetries of the universe. The classification of elementary particles provides a framework for organizing the vast array of subatomic particles and their interactions, offering insights into the fundamental forces that govern the cosmos. Experimental methods in nuclear physics encompass a wide range of techniques and technologies that allow scientists to probe the inner workings of atomic nuclei with precision and accuracy. One of the key experimental methods used in nuclear physics is nuclear spectroscopy, which involves studying the energy levels and transitions of atomic nuclei. By analyzing the gamma rays emitted during nuclear reactions, researchers can gain valuable insights into the structure and properties of nuclei. In fact, gamma-ray spectroscopy has been instrumental in identifying new nuclear states and understanding the dynamics of nuclear reactions. Another important experimental method in nuclear physics is neutron scattering, where neutrons are used to probe the structure of materials at the atomic level. Neutron scattering experiments provide information about the distribution of nuclei within a material, as well as the interactions between nuclei and other particles. Neutron scattering is widely used in fields such as condensed matter physics, materials science, and nuclear engineering. Accelerators play a crucial role in nuclear physics research, providing the high energies needed to study nuclear reactions and create exotic nuclei. Particle accelerators like the Large Hadron Collider, LHC, at CERN can accelerate particles to near light speeds, allowing scientists to recreate the conditions present in the early universe. The LHC, for example, can collide protons at energies of up to 13 tera-electron-volts, generating a vast array of particles for study. In addition to accelerators, detectors are essential tools in nuclear physics experiments, allowing scientists to measure the properties of particles produced in collisions. Detectors like the ATLAS and CMS detectors at the LHC are massive instruments that can track the trajectories of particles, measure their energies, and identify their properties. These detectors are crucial for identifying new particles, such as the Higgs boson, and testing the predictions of theoretical models. Nuclear physics experiments often involve collaboration between scientists from around the world, working together to design, build, and operate complex experimental setups. For example, the International Thermonuclear Experimental Reactor, ITE, project brings together researchers from 35 countries to develop fusion energy technology. ITER aims to demonstrate the feasibility of nuclear fusion as a clean and sustainable energy source, with the potential to provide abundant energy for future generations. The field of nuclear physics continues to push the boundaries of scientific knowledge, with new experimental methods and technologies driving discoveries and advancements in our understanding of the atomic nucleus and its constituents. The Standard Model of Particle Physics is a comprehensive framework that describes the fundamental particles and forces that make up the universe. One of the key components of the Standard Model is the classification of particles into fermions and bosons. Fermions, such as quarks and leptons, make up matter and have half-integer values of spin, while bosons, like photons and gluons, mediate the fundamental forces and have integer values of spin. The Standard Model predicts the existence of 12 fundamental fermions, including 6 quarks and 6 leptons, along with 4 fundamental bosons responsible for the electromagnetic, weak, and strong forces. One of the most intriguing aspects of the Standard Model is the prediction of the Higgs boson, which was discovered in 2012 at the Large Hadron Collider. The Higgs boson is crucial for explaining how particles acquire mass and is a cornerstone of the theory. The Standard Model has been incredibly successful in predicting the behavior of particles and their interactions, with many of its predictions confirmed by experimental observations. For example, the discovery of the top quark in 1995 at Fermilab provided further validation of the Standard Model's predictions. The Standard Model also predicts the existence of neutrinos, elusive particles that interact weakly with matter and come in 3 different flavors: electron, muon, and tau neutrinos. Neutrinos have played a significant role in shaping our understanding of particle physics and the universe. The Standard Model has been tested to high precision, with experimental results matching theoretical predictions to remarkable accuracy. However, the model is not without its limitations, as it does not account for phenomena such as dark matter and dark energy, which make up a significant portion of the universe's mass-energy content. Despite these challenges, the Standard Model remains a powerful tool for understanding the subatomic world and continues to inspire new generations of physicists to explore the mysteries of the universe. Quarks and leptons are the building blocks of matter, playing a crucial role in the structure and behavior of particles in the universe. Quarks come in 6 different flavors: up, down, charm, strange, top, and bottom, each with specific properties that contribute to the diversity of matter. Leptons, on the other hand, include particles like electrons, muons, and neutrinos, which do not experience the strong nuclear force. Quarks are bound together by the strong force to form protons and neutrons, while leptons exist as individual particles. Interesting fact, quarks have fractional electric charges, with the up quark having a charge of 2/3 and the down quark having a charge of -1/3. This unique property of quarks is a fundamental aspect of the Standard Model of particle physics. Another fascinating detail is that quarks are never found in isolation due to a phenomenon known as color confinement, where quarks are always bound together in groups called hadrons. Leptons, on the other hand, can exist independently and are not subject to color confinement. Interesting statistic: there are 3 generations of quarks and leptons in the Standard Model, with each generation containing 2 quarks and 2 leptons. This hierarchical structure provides a framework for understanding the properties and interactions of elementary particles. Quarks and leptons play a central role in the dynamics of the universe, influencing processes ranging from nuclear reactions to the formation of stars and galaxies. The study of quarks and leptons continues to be a vibrant area of research, with experiments at particle accelerators shedding light on the fundamental nature of matter. Nuclear reactions play a pivotal role in energy production, with processes such as nuclear fission and fusion harnessing the immense power stored within atomic nuclei. In nuclear fission, heavy nuclei like uranium-235 are bombarded with neutrons, causing them to split into lighter nuclei, releasing a tremendous amount of energy in the process. An interesting fact is that the energy released in nuclear fission is millions of times greater than that released in chemical reactions, making it a highly efficient source of energy. Nuclear power plants utilize fission reactions to generate electricity, providing a reliable and low-carbon alternative to fossil fuels. On the other hand, nuclear fusion involves combining light nuclei, such as hydrogen isotopes, to form heavier nuclei, releasing even more energy than fission. Fusion reactions power the sun and other stars, producing vast amounts of energy through the conversion of mass into energy, as described by Einstein's famous equation, E=mc². An interesting statistic is that the sun converts about 600 million tons of hydrogen into helium every second, releasing a staggering amount of energy in the process. Scientists are actively researching fusion as a clean and sustainable energy source, with projects like ITER aiming to demonstrate the feasibility of fusion power on Earth. Nuclear reactions also play a crucial role in the production of medical isotopes used in diagnostic imaging and cancer treatment. For example, the decay of radioactive isotopes like technetium-99m emits gamma rays that can be detected by imaging devices, allowing doctors to visualize internal organs and detect abnormalities. The field of nuclear reactions continues to drive advancements in energy production, medicine, and scientific research, offering a glimpse into the immense potential of harnessing the power of the atom. The future of particle physics holds exciting prospects for discovery and innovation. Scientists are exploring new frontiers in particle accelerators, such as the development of compact linear accelerators that could revolutionize the field. These compact accelerators have the potential to make particle physics experiments more accessible and cost-effective, opening up opportunities for research in a wider range of institutions. Another area of interest is the study of neutrinos, elusive particles that could hold the key to understanding the mysteries of the universe. Neutrino experiments, such as the Deep Underground Neutrino Experiment, DUNE, aim to unravel the properties of neutrinos and their role in shaping the cosmos. Interesting fact: neutrinos are the most abundant particles in the universe, yet they interact very weakly with matter, making them challenging to detect. The search for dark matter, another enigmatic component of the universe, continues to be a major focus of particle physics research. Scientists are developing new detection techniques and experiments to uncover the nature of dark matter and its interactions with ordinary matter. Exciting statistic: dark matter is estimated to make up about 27% of the universe's total mass energy content, yet its composition remains a mystery. The future of particle physics promises to unveil new insights into the fundamental nature of matter and energy, pushing the boundaries of human knowledge and understanding. In conclusion, the field of particle physics continues to captivate scientists and enthusiasts alike, with its intricate mysteries and groundbreaking discoveries. One fascinating aspect of particle physics is the concept of antimatter, which is composed of antiparticles that have the same mass as their corresponding particles, but opposite charge. Antimatter plays a crucial role in particle interactions and is a subject of ongoing research in laboratories around the world. An interesting statistic is that the universe is believed to contain equal amounts of matter and antimatter. Yet antimatter is rare in our observable universe. leading to the question of why there is an imbalance between the two. Another intriguing detail is the concept of quantum entanglement, where particles become interconnected regardless of the distance between them, defying classical notions of space and time. Quantum entanglement has profound implications for the field of quantum mechanics and has been experimentally verified through tests such as the Bell inequality experiments. Looking ahead, the future of particle physics holds promise for groundbreaking discoveries in areas such as quantum computing, dark matter detection, and the exploration of new particles beyond the standard model. With advancements in technology and collaboration among scientists worldwide, the quest to unravel the mysteries of the universe through particle physics is poised to continue, pushing the boundaries of human knowledge and understanding.